Okay, now we get into the more, I don't know, a little bit more in-depth things, a little bit more interesting, a little bit more than the basics. So we're going to talk about hierarchical data, right? And different ways of representing hierarchies and hierarchical data, which is a fun topic. And before I jump into the slides, I'm going to start a program in the background because it takes time. I'm going to start it ahead before I get, so it'll be ready by the time we get to that slide. So, the rest of the module, we just finished in sort of a generic introduction. The rest of the module is organized around these kind of three main areas. And so the next bunch of lectures will be focused on information visualization. That's kind of like part 2, let's say. This is like part 3, and that's part 4. If you think of like introduction as part 1, InfoViz is part 2, VolViz is part 3, and FlowViz is part 4. Just to give you an overview of how that's going to look like. Information visualization is all about abstract data. So that's data, it's very often stored in spreadsheets. And it's very often stored in databases. As opposed to scientific data. Scientific data is usually stored on a grid, a spatial grid, like a 2-dimensional or 3-dimensional spatial grid, or as an image. That's also scientific data. So we also call this abstract data. N-dimensional data means it can be an arbitrary number of dimensions. So you see in assignment 1, that's very high dimensional information visualization data. It has lots of dimensions. Right? You have disease type, you have age distribution, you have different NHS practices, you have year as one of the dimensions. It's big and complicated. So because there's no inherent spatial information associated with that data, we have to invent something. We have to create some space and some. Therefore, we have to choose a visual metaphor. Like, it usually is inspired by something from the real world. We're going to see a lot of examples of how we interact with the visual design. And there's a lot of focus on exploration as opposed to analysis, right, and presentation. In the scientific visualization context, we're looking at spatial data, right? It's usually 1, 2, 3, 4 dimensions. And the very important aspects are how do we project 3D information or 3D data onto a 2D space? How can we do that very fast? And often the focus is on analysis, and that means to confirm or refute a hypothesis. In the real world, so to speak, when you have a large, complicated data set, usually the people that collected that data set in this context don't really know exactly what kind of questions they're going to ask. They need answering. They want a tool that can just help them explore the data, see its characteristics, its errors, trends, outliers, and then based on their initial overview, then formulate questions like, I wonder if this is true. And that's called exploration. that's what happens over and over again. And the big question, one of the big questions is what visual metaphors do we invent or synthesize to represent this data and convey it in an effective way. And that's what the next lectures are all about. And that's also what assignment 1 is about. Right? How can abstract information be represented visually? How can high-dimensional data be depicted? Should we use 2D or 3D space in our representations? Where do we put the data? Like, how is it positioned? Right? And can we integrate something called focus and context? We're going to talk about that a little bit later, but that's related to, is some of the data more important than others? So not all data is of equal importance. And the question is, what is the most important? So a good interaction scheme provides different parameters that we can adjust and then modify what we're seeing based on input parameters. But the strategy is kind of always the same. And that's not written on this slide, but it's still important. The strategy is always as follows. Start with an overview of your data, a complete overview. Offer the user different ways of selecting subsets and filtering the overview. And then also provide details on demand. So when the user has decided on a subset they're more interested in looking at, they can ask for the details like the original data, underlying data for that special selection that they've decided is very important. So that's always the case, it's always the approach. So it's mostly interesting when the data is large and complicated, right? So how do we decide on mechanisms for selections of subsets? Right? Looking at large data sets usually involves some sort of aggregation. That means putting subsets into different groups that have something in common, and the extraction of metadata. Anybody know what metadata is? Did we already ask that?
Data about data.
Data about data, right? Think of statistics like minimum, maximum, average, first standard deviation, second standard deviation. Those are all examples of metadata. So we're going to see a lot of different kinds of data structures in this module, right? And the data structures are going to look like things like hierarchies and graphs and other kinds, lists, plot-based, and they're all going to have their own limitations, strengths, and weaknesses. However, one thing they're also all going to have in common is the ability to find patterns. Right? Has anybody ever thought about the word intelligence? The word intelligence gets used a lot, like I'm intelligent or he's intelligent, or this person is smart. Artificial intelligence. Has anybody ever wondered what that word means? I mean, this is something I think we all wonder about sometimes, especially when it's time to take a test. Like, does a test really measure my intelligence? Does my IQ, is that a reflection of my intelligence? I think we've all wondered about this. I think not only I have wondered, like, what is intelligence? Has anybody else wondered, like, what is intelligence? Like, kind of thought, what would be a good definition of intelligence? Anybody want to take a guess at that? I'm guessing that your answer is not your IQ score. What do you think a good definition of intelligence is?
But when we say that someone is intelligent, we basically mean that they have more knowledge than us.
They have more knowledge, so how much knowledge you have. Okay, what would you say, Gabriel?
If you're presenting the same decision multiple times and make a different choice in a non-random way.
And that's how you would define intelligence? So a person that makes the same decision consistently is intelligent?
No, if you can make a different decision based on the same scenario in a non-random way. So a computer is programmed, it will always...
Okay, I see. I think I get the idea. I always thought, like, with your answer about like how much you know, I always wondered, like, am I kind of, well, this was when I was a child, am I stupid because I cannot remember everything I need to remember for this test? So I would say that that is a kind of intelligence, the ability to recall. But it's not the most interesting kind, at least not in my case, because I'm not very good at memorizing things and recall. And that's not my... Decision making is a very good definition, actually, the ability to make good decisions. Very difficult to evaluate whether somebody has made a good decision or not, because how do you decide when something is a good decision? It's sort of like deferring the question to another question. The best definition I've ever seen of intelligence, because it could be a long discussion, is this, the ability to find patterns. I heard somebody, a professor, describe intelligence as the ability to find patterns, and I think this is a great definition of intelligence. And you'll find that a lot, we talk about this kind of a lot, you know, the ability to find patterns, and we're always looking for patterns. It's a really good definition, right? So it adds some interest to the whole discussion. Now, this module is not really about necessarily depicting data per se, but it's only interesting if it's a very large and complicated data set. So it really could be called big data visualization. It's not very interesting. We don't need special methods for small data sets necessarily. But we may need some techniques for subsampling or subsetting, right? That's when the user wants to select a subset or a smaller range of data that they're interested in. We may talk about segmentation techniques, different ways of grouping data into different categories. And I think that was a big topic in the visual analytics class, right? How to group data into different categories. Or compute the similarity of data points. That's another way of saying that. And aggregation techniques, ways of generating metadata that represents a group, right? And we're going to see examples of all these things as we go along. So let's look at some examples and we'll start with the hierarchical data. Can anybody think of a very common source of hierarchical data that you sort of encounter on a daily basis? I think that's a question that most people could answer. What's your name again? Nate. Family tree. Your family tree? Yeah, that is definitely a source of hierarchical data, but you don't, well, no, I don't look at my family tree on a daily basis. It would be kind of cool. Any other sources of hierarchical?
Folders on PC.
Exactly. Your files and folders on your laptop or your PC or whatever. That's a very common source of hierarchical data, right? You have a root folder, and then you have files and folders inside of that, and so on. Has anybody ever lost files on their hard disk? It's very easy, isn't it? It's very easy to lose stuff. Because the bigger it gets, the more easy it is to lose things and get lost. So we're going to look at some conventional approaches to hierarchical data representation. Then I'm going to look at tree maps and we'll look at some examples. So this is the kind of data we're looking at. There's some sort of hierarchy. And the naive representation is a tree. Like this is a tree. It's ordered acyclic. Anybody know what acyclic means?
Does it go back to the parent node?
There are no circles. That's right, there are no loops. Right, it's hierarchical, obviously. That means there are child nodes and there are parent nodes. The subnodes are both children and parents. So that's, I think everybody gets the idea there. And this is one of our favorite hierarchies, the management hierarchy. Like everybody has a boss kind of thing. It's not a very exciting example of a hierarchy. But anybody see sort of a limitation with these kinds of tree representation already?
Maybe if it's too much data, everything just gets crammed so much.
Exactly. What's your name again?
Alyssa?
Alyssa?
Yeah.
That's right. We're only looking at something like 12 data samples. I don't know, maybe less than 20 right there. And it's already occupying a huge space. It would be challenging to apply this to your hard drive, for example, right, and see all the files. It's possible, but it would be challenging. This is a hierarchical representation right here. This is like a file system window. This is sort of what we see every day as our visual representation of a hierarchy. It's not very exciting either, is it? Everybody's seen this is the Macintosh one. You've all used either the Macintosh or the Windows file browser. Right? It is a hierarchical visual representation of your data. And they're difficult to use, aren't they? I mean, it's easy to have things get lost in there. It's very easy. And the number of files and folders that I can see at the same time, I don't know. It's good when it's like 100 or less. But if we get into the thousands or millions or billions, it's not very effective anymore. This is another kind of hierarchy, a word tree hierarchy. And the idea is that you see a set of nodes, but you only see the child nodes if you click on one of the parent nodes. So if I click on a parent node, then it expands and shows me the child nodes, and I can recurse. So I'm only seeing the things that I click on. Venn diagrams are another unpopular way of representing hierarchical data. They can be used to represent hierarchical data, but they're not a very common choice. Right, so in this example, right, rational numbers are a subset of real numbers, and integers are a subset of rational numbers. Irrational numbers are also a subset of real numbers, and so on. So that's kind of it's another kind of hierarchy, right, or hierarchical representation. It's not very popular, but it can't. Venn diagrams are very popular, by the way. So everybody here has seen a Venn diagram before? They're just not usually used to represent hierarchies very often. They're usually meant to represent overlapping subsets. Like two circles overlap partially, means they share something in common. So another method is called a tree map. Anybody here who's seen a tree map already? I think some people have. One person? Anybody else? I think some people have too. How about visual analytics? Were tree maps discussed in the visual analytics class?
Briefly, yeah.
Okay. So everybody that took visual analytics knows about tree maps already? Good. We're going to have another brief introduction. You can compare the two and see like which one is, I don't know, more exciting. So remember that hierarchical tree we saw in the first example. Here's another hierarchical data set on the left. And this is the tree map representation of that same data set. So the question is, how is this same information from this side also encoded on this side? These two represent the same information actually, but they look very different, don't they? So this is our root node of the tree map, and that root node is mapped to this whole rectangle here. So it's called a space-filling approach to hierarchical data representation. So we can take the whole screen and map it to a rectangle, and that's the root node. And that root node is subdivided by its number of children. So the root node in this case has 4 children, 1, 2, 3, 4. This is a leaf node, it's 12. And that 12 gets mapped to this rectangle right here. And it has no children. It's already a leaf node, so it doesn't get subdivided any further. The next one is the 8. That 8 gets mapped to this rectangle right here. Right. It's hard to see, but this rectangle is a little bit thinner than this one. This one's a little bit thicker than this one. What happens to the next children? Here's another child node of the root node, and it has 5 children, 2, 2, 3, 1. That rectangle is mapped to the next one in line. It's that rectangle and that rectangle are mapped equivalent. And because this is an internal node, it gets subdivided by its own children. So 2, 2, 2, 3, and 1. Those are all leaf nodes. And the size of the nodes represents the data that they're storing, right? Represents some value. This rectangle is smaller than this one, right? This is representing 1 unit, and that's representing 3. What about the next child? That child is this rectangle here, and it has 3 children, these 3. So the 6, 8, and 11 are represented here, right? This. And then the leaf nodes 6, 8, and 11 are mapped here. Then we have a long, thin 5. And then we have a big 40. So that's the tree map equivalent of this hierarchy. Did everybody follow that? I didn't explain how the layout algorithm works, actually. There are lots of different layout algorithms. And I would explain it if I had a marker, but I forgot a marker today. And I hope I remember to bring one next time. Here's another example. This one is a little bit confusing because you cannot see explicitly the relationship between parent and child nodes explicitly. You have to sort of deduce the relationship. This one is showing the relationship between the parents and the children explicitly by adding padding. between the child and the parents. That's our parent node, A162, occupying the whole space. And then there's some padding. So we know that B10 is a child of A162 because there's a pad around it. In C30 we can see is a child of A162 because of this padding. Right? And then D62 is another child, but it's been subdivided. And then the padding indicates, okay, there are 3 leaf nodes here, and then N28. So there's a pad, a space of padding between the children and the parents that makes it explicit, like the parent-child node relationships. Everybody with me so far? Now those are small examples, but they're just so you get the idea. So when you see a tree map, you know how to interpret it. And I will bring a marker next time so I can give a demo of like one example construction algorithm. Here are some more examples, and this is very similar to the one I gave in assignment 1. This is a larger data set, and it's a data set of cars. So cars and their manufacturing. And in this case, the size of each rectangle of the bottom, the leaf nodes, is mapped to retail price. And they're grouped, so they're grouped by vehicle name, the manufacturer, and then the country of manufacturer, right? So I can see different countries if I look closely. Here is the US and all the cars that it manufactures, right here. This is Germany, right, mapped to this rectangle. It's subdivided by make of car and then vehicle name. And there are some other countries here. Japan is there, Sweden is there, and South Korea is there. I didn't even know that South Korea produced cars. And then the color is mapped to price. So the more expensive cars get the darker brown, and then the less expensive cars are like white, right? So you can see right away, for example, that on average, Japan has the cheapest or the lowest retail price cars, and Germany has the most expensive ones. You can see that in a second by looking at this. And the US has sort of a mixture. Oh, this is the UK. I overlooked this. The UK has very expensive set of cars too. That's not too surprising. In South Korea has the ones that are the least expensive, very least on average. And so those are some of the things that you can see right away from this tree map very, very quickly. Here's the live demo example. So I started this program before. Anybody ever wonder where your disk space disappeared to? Yeah, I have that problem all the time. In fact, I'm not even joking. I got an error message on Friday afternoon, which is when I get the most error messages, saying your disk space, your backup disk space is out. We can no longer perform any backups. I just got that on Friday, so I reformatted the backup and started over again. Anyways, this is a program. It's called Disk Inventory X. It's a tree map of your hard drive. It's free. You can download it. There's a Windows version. It might not be called Disk Inventory X for Windows.
It's called WinDirstat.
WinDirstat?
Yeah.
Okay, I think there are multiple versions for the PC.
It produces the same result.
Okay. There's another one for the PC called Sequoia View as well. They all look very similar to this. Each bottom level rectangle represents a file on your disk. Right? And those files are obviously stored in folders. And as I move my mouse around, it will identify the path and the file name in the status bar. Right, so there's the traditional hierarchy where I can't see all my files, and then here are all my files. So these are all multimedia files. So if I want to free up disk space, I should get rid of these multimedia files. But it's also kind of fun to see, like, oh, I have these like thousands of tiny files. Like, what are those? You know, it's kind of fun to see like what they are. In this case, those are research papers. That's a collection of research papers from a journal. Yeah, so this is all research papers for me. This is all audiobook files, book chapters, things like this. This really big one is the iMovie folder, where it's the iMovie library folder. So it's free and fun to use. So it's a very good example of a real tree map being really used, and it can visualize millions of files. If I want, I can select a folder, double click on that, and then the whole space will be occupied by only that folder, and I can drill down into the hierarchy. This happens to be just an overview. Okay, I'm getting conscious of the time now. Just one more slide. Yeah. The nice properties of tree maps is that they're space filling, so they use the whole screen space, they distribute the representation of the whole screen space. They can represent hierarchical data, which is nice. They can also represent more than one variant or multivariate data. And they apply to massive hierarchies, arbitrarily large hierarchies. Just some things to note that they don't include generally geospatial information and neighborhood preservation, so you cannot guarantee which nodes are going to be next to one another, finally, generally speaking. Any questions about that? Okay, we'll stop here then. Happy Monday. I survived.